Modular equation. And what we're going to do is mimic the way we do it in real arithmetic. So suppose you had this equation in real number arithmetic, 3x equals 4. What we would do is multiply both sides of this equation by the multiplicative inverse of 3, which I'm going to denote by 3 to the minus 1 times 3x equals 3 to the minus 1 times 4. And multiplicative inverse is, by definition, the product is 1. So this is 1x. We happen to know that 3 to the minus 1 is 1/3 times 4. So the solution here is x equals 4/3. Now, how do you do that in the modular world is you basically mimic the same thing. So we have 3x congruent to 4 mod 7, and we want to find x. Well, we've previously calculated what the multiplicative inverse of 3 is, but whether we've calculated it or not, since 7 is prime, we know 3 has a multiplicative inverse, because every number is going to be relatively prime to 7. So we can do 3 to the minus 1, interpreting that as mod 7, times 3 times x is congruent to 3 to the minus 1 times 4 mod 7. 3 to the minus 3, the multiplicative inverse of 3 times 3, of course, will be 1. So that's 1x is congruent to the multiplicative inverse times 4. So we just have a calculated solution, except the fact that we need to know what the multiplicative inverse of 3 is. And in the previous example, that was calculated to be minus 2 mod 7. So we can plug minus 2 in. By the way, minus 2 is not in the range 0 through 6. So I would, instead of calling that minus 2, I would call it minus 2 plus 7, which is 5. So, but, I mean, minus 2 and 5 represent the same number, modulo 7. Anyway, so I would write this as x equals, you can say minus 2 or you can say 5 times 4 mod 7, which is 20 mod 7. And usually, again, you want a representative that's in the range 0 to 6. Subtracting 14 from 20 gives you 6 mod 7. That's probably the way that you would leave it. It's x is, the solution is 6. X equals 6 is the solution to the equation 3x congruent to 4 mod 7.